Yes, you can start now.
Okay, sir. Good evening, everyone. A warm welcome to all the dignitaries, faculty members, industry professionals, and dear participants present here today. It is truly a pleasure to have such an enthusiastic audience gathered for a session that focuses on innovation, sustainability, and the future of mobility. Today's ninth session of ATAL FDP discuss bring together technologies, intelligence, and electrical and refocused shaping the next generation of transportations. Smart EV architecture, components connectively, and AI intelligence. Electrical vehicles are no longer just about batteries and motors. Modern EVs are intelligent systems where multiple components communicate seamlessly to deliver performance, safety, and efficiency. In this session, we will explore how smart EV architectures enable strong connectivity between powertrain components and control system and cloud platform, and how artificial intelligence plays a crucial role in optimization, predictive maintenance, and drive behaviors analysis and overall vehicle intelligence. This topic gives us clear view how EVs are evolving from mechanical machines to smart connected and direct data driven mobility solution. It is my great privilege to introduce our esteemed guest speaker, Mr. Pawan Joshi, a seasoned industry professional currently working with Tata Motors in the Advanced Engineering Department. He is an accomplished data analyst and AI/ML engineer with strong expertise in analyzing data-driven intelligence to automotive and electrical vehicle system. Mr. Pawan Joshi holds a bachelor's of engineering in electrical and electronics engineering from DIT University, followed by an MTech in power system from the National Institute of Technology Warang, and also a master degrees in physics from YCMOU University, reflecting his strong analytical and interdisciplinary and academic backgrounds. With a strong blend of industry experience, data science expertise, and domain knowledge in power and automotive system, Mr. Pawan Chowdhury brings valuable practical sights into how AI and machine learning are transforming the automotive and electric vehicle industries. His experience is bridging theory with real-time industries and the applications makes him a highly relevant and impactful source person for today's session. On behalf of the entire organizing team, I extend a warm and heartfelt welcome to Mr. Pawan Joshin. Sir, we are delighted to have you with us today and looks forward to your valuable insights on smart EV architectures and AI integrations. Without further delay, I invite Mr. Pawan Joshi and Mr. Kodandaraman take over the session.
Good evening, everyone. I hope so. My voice is audible.
Yes, sir.
Yeah. Let me know whether my screen is visible. Is my screen visible?
No.
No, Raman. Yeah.
No?
Yes.
Ah,
Yes.
yes, visible.
Yeah. So, good evening, one and all. It is a great moment visiting PS and ACET once again. Here in today's topic is we are going to discuss about what are the future trends in EV and how EV architecture is slowly evolving, and what are all the various components in EV, what are all the challenges in it, and how AI comes into picture in each of these components, in each of these area, and how it improves the user experience in a automobile industry in a EV vehicle. So myself, Kodandaraman. So these are all the contents. We will start with the evolution, then talk about what is SDV and what are the challenges involved in it. Discuss about the various components, protocols involved, and AI. So, like discussed in the previous session, the automotive industry, the vehicles had more mechanical parts in the initial stage, and later on it moved towards an electrical era where everything became electrical and electronic components were used. And later, now the future is a software-driven vehicle. So, what is a software-driven vehicle? So, in basic sense, the vehicle is more software dependent than hardware dependent. It is more decoupled from the hardware dependency. So, how is it possible? Like, what is a software defined vehicle? So, for a simple example to say, we all have a mobile, and there are various applications in our mobile, like Netflix, Prime, or any other shopping applications or no. So all this are installed in our application or used based on our need. We use for we take a subscription of Netflix or Hotstar just for a month, and then we don't use it. We That makes that mobile capable of using Netflix, but it depends upon the user whether to subscribe to it or not. Similarly, in a vehicle, the various advanced feature which are given in the vehicle need not be always given to a customer for the full time. It can be subscription based. The vehicle itself can be upgradable, like how OS updates are given in Android mobile. The features of the vehicle can be upgradable. This makes the vehicle more hardware independent and more software dependent. This makes the vehicle more flexible. Supposing a driver is going for a long drive and he needs the ADAS facility like land departure system or a cruise control system just for a week where he is doing a long distance travel. So he can subscribe to those features only for that particular time alone. Whereas the sensors, the hardwares which are used are still there. There is no change in the sensors and the cameras which are used for the ADAS features. It is used whenever it is necessary. Reverse parking system and automated parking system is or these are all one of the examples. So this makes there are two benefits out of this. The customer himself gets a premier feel where he has to go for a he gets it when he needs it. Otherwise, he doesn't subscribe to it. At the same time, the vehicles are also more like the OEM also, the vehicle owner, like the vehicle equipment manufacturer, also gets an advantage out of it. He also gets a subscription based income rather than his profit stopping when the vehicle leaves from the dealership. He also gets an income based on these subscriptions and services, which are provided even after the vehicle goes to the customer. So these opens a bigger this concept opens a bigger market, and also it comes with a lot of challenges. What are all the challenges involved in it, and this how is this features made possible? So as of now, if we see the overall E&D architecture in a vehicle, they are more controller dependent. There are separate controllers for each and every function. There is a separate controller which takes care of powertrain, a set of sensors for it. There is a separate controller which takes care of the body control module. Body control module, I will explain it in the later slides as well. So there is a domain based approach. So now what comes into picture is a central zone based approach where various functions are coupled together. There is a central HPC. HPC is a high processing compute, you can say, like the HPCs which are there in our laptops and mobiles. So there is a high processing compute which acts like a brain for the car, and there are multiple zonal level, area level ECUs or controllers which takes care of the zonal level controls. The front part of the body is controlled by a separate set of uh, like zonal ECUs. And how the software architecture changes here. Yeah, initially, we used to follow a V-shaped validation and verification model, where the requirement is given and accordingly the vehicle is tested and given to the supplier, like given to the customer. Whereas now, there is a DevOps kind of cycle which is required, where the vehicle continuously is updated, tested, deployed, and then released. Again, it is coming into a update because different set of features are being updated in a vehicle. So it changes the whole perspective of the vehicle from ENDV architecture to a software architecture. So there are also challenges which comes into this, because as far as there are more softwares involved, and as far as connectivity is involved in a vehicle, there are more and more cybersecurity concerns involved in the vehicle. The cyber security part, the software updates which are provided to the vehicle, the VOTA updates which are provided to the vehicle has to be secured, for which the IT cybersecurity comes into picture, where the security in the vehicle has to be upgraded up to the level of our laptops or website security, or our mobile application, banking application security, where the customer's data has to be protected. The softwares which are updated in the vehicle, those software has to be protected. So a digital signature based photo update, where a specific a set of vehicles are updated at one particular point of time through an authenticated process. The cloud which provides the update to the vehicles, those are also those things also have to be secure. You would have seen many videos even in the YouTube, where a set of automotive cyber hackers, white hat hackers, have hacked the entire car, and they are able to take control of the car, like uh, using Wi-Fi modules which are available in the infotainment system, and the OBD ports which are available in the cars. They were literally able to take over the car, access the steering, brakes, everything of the car. You would have seen it in recent movies as well. So this is not a far future. It is actually happening. It is the cyber attacks are actually happening. So the OEM has to develop a different set of framework which is required for this cyber security, and using AI, how to conduct penetration testing in a vehicle, how to improve the cyber security using AI. Those are also a broader perspective, which opens the market for various domains in the automotive industry. Like we know, these are all various components in the vehicle, and each and every component uh, can be software defined, and each and every component has a scope for AI in it. So these things will be explained by Mr. Pawanjosi in future slides. So basically, these are the various. We can segregate the component into low voltage components and high voltage components. High voltage components are related to the powertrain, whereas low voltage components are related to the uh, voltage which are about 12 to 24 volt, where our telematics controller, body control module, which takes care of the lights, door locks, wipers, windows, comes into picture. Instrument cluster, which displays the speed, battery SOC, the range, mileage, any seat belt warnings, and infotainment. There is also anti-lock braking system, which prevents the car from skidding. The vehicles it protects the braking mechanism of the vehicle, and also the ADAS features, which consists of various other features. It's inside itself: adaptive cruise control, lane keeping, collision warning. So all this comes under. low voltage components. AI is not restricted to high voltage alone or low voltage alone. It plays a major role in every single component which is there in a electric vehicle. So when high voltage components comes into picture, there are battery management system, and as well, of course, electric motors, motor control unit, and the inverters which are required for DC to AC conversion, and battery coolant system and onboard charger. There are AI and software level updates required in each and every component. Depending upon the driver's driving behavior, you can suggest the powertrain pattern for a driver or for a vehicle, which can improve the mileage of the vehicle. Depending upon the terrains, you can modify your software so that it will give a uh, high torque and high premium experience driving during, depending upon the terrains. So there are multiple use cases in it, which will be shown in the further slides. And all this is possible through the in-vehicle protocols which are coming into picture. CAN, controller area network, which is defined by Bosch, and which is the backbone of whole automotive industry's communication protocol. Every vehicle which we are seeing now in the uh, roads are communicating within itself through CAN and CAN-FT. And there is also automotive Ethernet coming into picture. When a high processing compute is needed, the transfer of data between multiple electronic control units has to be faster, for which Ethernet is needed, because the maximum speed of a CAN based bus is only 1 Mbps, whereas Ethernet you can go up to GBs. So when cameras comes into picture, radars comes into picture for ADAS, and when software updates are there, so there will be a large amount of GB of data required, and the transfer of data has to be faster, because it is highly safety critical when ADAS comes into picture, and the processing of the data has to be faster. So for all this, high processing compute is also required in the vehicle. So just a minute. Hello. Sorry, there was a technical glitch. Pawan, I guess you can take it from here on. Let me know when my screen is visible.
Yes, Raman. Am I audible, Raman?
Yeah, you are audible. Is my screen visible?
Uh, just waiting. Yes. Yes, Raman. It is visible now. So
Yeah.
thank you everyone for this generous introduction. Yes, and thank you, Raman. So today we will see in the remaining part all the aspects of AIML, as well as prognostics, that how much important prognostics is and why we are going for it. So as you can see in this image, uh, you can see that means prognostics like overheating of engines. We know there are sensors all over the vehicle and the data is coming in the cloud. So we need some algorithms which can predict the upcoming behavior of any sensor, any component based on the previous data. So that is a general definition of prognostics, that we need to predict that when the vehicle is going to get filled, so that we can be ready, um, so that we can be ready, so we can take the appropriate action. So there are multiple components, but the way prognostics work is more or less same. That I will explain in the further slides. Raman, next slide. Raman,
Yeah, I have changed the slide. I don't
wait,
know
wait.
whether there is any issue.
Now it is reflected. Yes.
Yeah.
So, on a broader aspect, when we see, there are multiple benefits of AI in any industry actually. So specific to automotive, we will see. So regarding that, improved safety, how improved safety in terms of lane departure, autonomous emergency braking, we know, and adaptive cruise control. Second is the predictive maintenance, enhanced driver experience. This all means in some way or another, we based on the vehicle data, based on the camera and lidar, whichever are present in the vehicle, we take images, and all these lane departure warnings. So everything, everywhere, AI can be used. So autonomous driving, ADAS, and cost saving is one of the factor which, using AI, we can achieve. Raman, next slide.
I guess so. It
Yes.
is taking some time.
Yes, yes. Yes, it is taking some time, but okay, yeah, it is reflecting. So we can use, means this slide will tell about the use cases of AI. Driver assistance, like reverse parking, when we are trying to park the vehicle in reverse direction. And this is also one type of UI case. Autonomous vehicles, we know ADAS, like Tesla has autonomous vehicles. Driver monitoring system, it is called a DMS, a driver monitoring system, which tells the which constantly monitors the face of the driver, the body position of the driver. Actually, we have tested this DMS system in our trucks and other vehicles. So where we ask the driver to wear the glasses. So it will, so if there are type of glasses in which the eyes of the driver are not visible, at that time also this driver monitoring system will give a alarm, because driver monitoring system is constantly monitors the face of the driver. If there is if it feels like that eyes are closed more than like few some particular time, uh, it will start a buzzer. If the driver is distracted, like he is bending his head to right side of the window or left side, then also there are multiple types of warnings in driver monitoring system. So so every time means it is completely a machine learning based system. So the models are trained for, means what should be the correct posture of a driver, and if anything goes beyond that, it will detect it as a faulty system. So it gives the, after that it raises the alarm of driver drowsiness, sometimes if driver is yawning. So every type of activity is modeled in the driver monitoring system. So AI in manufacturing. So actually, it can be used. Artificial intelligence can be used. Just we need to find the use case how we can use it. But most of the places we can use personal assistant, passenger experience, supply chain. So this is a general slide, and we can say we can use it. So Raman, can we go to next slide?
Yeah, I've changed it.
So this is a particular use case I will tell you, and what is the problem definition, why we are going for artificial intelligence and machine learning. This is a sample, as we know that there are multiple sensors inside the vehicle. So every sensor is generating data at a very high frequency. That high frequency is required inside the vehicle. So, but what happens when we send that data to the cloud, that we cannot send the data with the high frequency to the cloud, as we need to pay the cost for the cloud. For every single data point, we need to pay the cost. So whatever the server we are using, if we are using very high frequency, if we are sending very high frequency data to the cloud, we need to pay more. So even though inside the vehicle data is flowing in very high frequency, in milliseconds frequency, but in cloud we need to send like 1 minute data, the data at the frequency of 1 minute, like this. So this is a simple telematics data which you also can get. It is means publicly available for if you want to try any machine learning algorithm, if you want to try any type of algorithms, you can download this data. I think in NASA website also there are some there is some data regarding the battery and other things, so you can find this sample data. So this is a typical type of this is a typical data of a vehicle which comes in this format. So first of all we need to understand how the data comes from the vehicle. So the second thing is this data does not contain any patterns. So we need to find pattern. We need to find the pattern in such a way that we can use that pattern in order to tell something. In order to, like it is written, it can be absorbed in design cycles. We can use this data to change, to do some modifications to the design. So the problem statement is that we are getting hundreds GB of data per day and we are not able to use it. This is a general problem statement for any automotive industry. So we should know how to use the data. Okay. So how, Raman, next slide. So how we should use this data?
Just a minute.
Hmm.
I guess there is some network issue.
Okay. Maybe Raman, you can turn off your video. The bandwidth will be saved, and I think.
Yeah.
Or should I close my video?
Yeah, I am turning off my video. Is the screen visible?
Yes. Now it is visible.
Yeah.
Yeah. So what is the solution? So we know there is GBs of data coming every day, and what we can do. So we need to bring out some important aspect from that data. Okay. So what we need to do is that we need to find some details. We need to find some failure cases from the supplier or dealer, and based on the data and the information from the supplier, we can tune to some algorithms and some driving styles we can perform. Yes, next slide, Raman. So okay, so there is this is actually a famous technique. Everyone uses that in the same way whenever there is a time series data or any data. Like in case of satellites, also in case of telescopes, also we can see where the data is continuous in time. At that time, we have to find some techniques to deal with the data. So this is called window and strider. So we kind of, for a time series data, we make windows. So if we have a long time sequence data, so we make small windows of the data. Raman, next. Yes. So for every window, there is this is actually called feature engineering in terms of machine learning. That for every window, we need to because we cannot take the instantaneous values, so we need to take some average, because average data keeps kind of good mean, like we can say mean the mean data keeps the correct information more or less. Okay. So for every window what we are making, we will take some mean of all the quantities whichever are present in the data. Next, come on. Then what we do, as we know that this is a continuous time series data, so we need to use kind of recurrent. We know what is recurrent neural network. Recurrent neural network is a type of neural network which uses the information of the past window, because we know that data is continuous in time. Data is the past window is related to the next window. As the vehicle runs, the battery voltage decreases, so every single point in the time is related. So we need to use recurrent neural network. So the information of one window is sent into another window. Okay, so recurrent neural and any other type of neural networks also we can use. This is just a use case. So yes, so Raman, just wait in this slide. So based on this information for one vehicle, we create one vector. What we call it, it can be any dimension. We suppose we are making a 64 element, 64D vector. So for one vehicle, for complete duration, we will make one vector. Raman, next slide. Yes, so this one vector for one vehicle will contain all the information of the vehicle. So its driving pattern, the way driver drives the vehicle, harsh acceleration, braking, and all these things. So what happens that every vehicle will have now one vector. So currently in the screen, I am showing it is in 2D. This is a 2D image, so I am showing the point in 2D, but actually it is a 64 dimension because the vector we have created for the vehicle is a 64. So we cannot imagine that, but for machines it is not complex. They can group the things in any dimension. So 64 dimension vector we have created. So all the vectors which are of same pattern, which contain same pattern or same type of information will come together. So if the driving style if the driving style of two vehicle is very much similar, then these vectors should come closer in space. So this is the latent space, so these vectors should come closer. Next. So, so what will happen is that every vehicle has a vector, 64 dimension vector. So finally all the vectors come close. So you will find that few type of vehicles are moving together in some sense, like clusters are getting formed. So this is the only point. Means this was the main purpose. So what we did here is that now we will see whatever the faults are coming in the vehicle. We will see what type of fault. Suppose in the cluster 3, all vehicles are facing some problem related to the brake. Means there is something in the cluster. Means in cluster 3, all the vehicles, suppose you so all the vehicles are getting driven in a way that all are facing this brake issue. Or somewhere, if in some cluster, if we have found the issues of engine in both these two vehicles, means there is some problem with these driving patterns or the area where they are getting driven. So like this, we will form the clusters of the vehicle, and we will come to know that which vehicle lies in which category, and this vehicle can be chances that this vehicle we will get faulty. Means this vehicle can get engine type of fault or brake type of fault and some other. Yes, Raman. Next. Okay, so this was what we are doing is that we are using algorithms, so deep learning algorithms. So recently we have published one paper also. So this is a digital twin for motor and MCU incorporating deep learning algorithm AIML using intelligent prognostics for electric vehicles. So recently, just I think 10 to 15 days back only it got published. So this is a paper where we are using a technique called autoencoder. Autoencoder is a technique which we are using for anomaly detection. So as we know there are IGBTs inside the MCU. So and we know that there are sensors everywhere inside the vehicle. So we know temperature of more or less each and every component inside motor and MCU. So what we do is that we monitor the temperature of the IGBTs, because once the IGBT fails, we know that there will be no switching, there will be no DC to AC conversion, which is required for running the motors. So these IGBTs are very crucial. So other components also, but currently we have focused here in IGBTs. So we monitor the temperature of IGBTs, and we try to find the pattern. So we have trained here. We have used the autoencoder model, and we have trained the model with the good data. Good data means when we know which is the at that time the IGBT was behaving normally. So we know the temperature patterns when the IGBT was behaving normally, and we also know the time when the IGBT failed. So we have trained the model with the good data. So the model understands what is the good data, how the normal temperature ranges looks like. So whenever there is a chances that IGBTs, the temperature is shooting in the IGBTs, so that model, the autoencoder model, will generate a error. So that is called construction error, I think, reconstruction error, sorry. So that is called a reconstruction error. So that reconstruction error goes up, so it kind of gives some early indication that there is something abnormal going in the vehicle. Maybe the coolant is not working properly. Reason can be anything, we need to find that also, but at least it is telling that IGBTs are going above their normal temperatures. So this particular paper uses autoencoder. Another another algorithm and another type of faults we are using CNN plus LSTM. So these are we are using these because this is a time series data. So every time whenever we have a time series data, we need to use LSTM type of models because we need to form the windows the way I was telling you in the previous slide. Okay, and so LSTM, generally we use LSTM algorithms. So before going into any modeling, so we need to first understand what the automotive data looks like. So for that, you can download whatever is the publicly available data of the automotive. CAN data you can download, and telematics. There are two types of data: CAN data and telematics data. CAN data is controller area network, which is also, I think it will be available somewhere. And second is this telemetry data. Telemetry data, telemetry data is that GPS locations, speed of the vehicle, and the fuel. What is the fuel or SOC in terms of ICE vehicle? It is fuel, and battery vehicle SOC. So these are general data, means which is readily available. So this is called telematics data. So CAN data is regarding some motor, all the data of the motor, like the angle, what is the angle of the resolver, what is the speed, what is the torque, what is the regenerative torque, torque estimated, all these kind of data which is particularly related to motor, MCU, DC auxiliary inverters are there, steering motors are there. Everything comes under the controller area network, CAN data. So now there are two things. One is cloud based data, second is edge based data. Edge based data is, you can understand, like this CAN data only. So edge means any ECU, we called any ECU. There are multiple ECU like BMS, battery management system, like vehicle control unit. These are called ECUs. So we call that edge based. So any algorithm if you are running inside the edge, it is called edge based algorithm. Any algorithm we are running on the cloud, it is called cloud based algorithm. So the type of algorithms where the frequency is not a concern. So we need to go, because we know in cloud the frequency, we cannot go with very high frequency in the cloud. So there are two different types of algorithm we need to make based on our what is our purpose. So data frequency, the same what I am explaining. Raman, next slide. So prediction is like this, you can understand this. So suppose the last bit, it is the day of the failure. Okay, so what we do is that suppose this is 14 days of data. So the failure came on the last day of failure is the 14th. So what we will do is that we will pick the seven days, previously 7 days we will pick, and we will mark those all 7 days as level 1. Level 1 means you consider as a fault, level 0 means healthy. So we will train, we will means we need to make a output column with the complete data, and we will mark it as 1. So there are again there are two techniques where we can mark the day of failure 1, then the just one day before 0.9, before that 0.8, 0.7. That is called smooth labeling. Or else you can directly mark complete 7 days data as 1, that is faulty. So both are means their use cases. So like this only we are doing the CNN plus LSTM, what we are working currently, but we haven't cracked because it is a bit difficult to run it completely. Raman, next slide. So this is a paper where we have explained the electrical aspect. This paper I and my two colleagues wrote in 2023, and we wrote this. This is regarding what we did here. We simulated the electrical aspect of a electric vehicle. So, this a research paper. You can read this. It contains all the what was the problem statement, why we went for this. Actually, what was happening in the field, that so whenever the driver was reaching in the charging station for charging the vehicle, and suppose the vehicle is not getting charged, so at that time there was a confusion between the supervisor or the person who was there at the charging station and the driver. So the confusion was driver, from the perspective of driver is thinking, or driver thinks that if the vehicle is running, means there is no fault in the vehicle is okay. But charger person also gets confused when he tries to charge the vehicle and vehicle is not getting charged. So at that time, knowing where exactly the fault lies, because so this was actually a problem. For that, we need to make a small model. So what we did here is that we made a very small model of replicating the electrical characteristic of the, not the mechanical characteristic, replicating the electrical characteristic of the electrical vehicle. So we around very small model it was. Maybe once you will go in the research paper, you will come to know. Whenever we plug so suppose any vehicle bus is facing issue, so at that time we used to plug that charger to that small bus model. So if that model is getting charged, means there is no issue from the charger side, because that was the kind of proof for the charger that charger is charging. If that charger can charge the small model electric bus model, then it should charge the bus also. So there are chances that fault lies on the bus side. So all the aspects you can go if you are interested in this, but it contains so much information about the charging gun, and about these all the tests we have done: insulation test, power assessment test, and communication test. Next slide, Roman. Okay, so this is a problem of moving mass. It is kind of a very long pending problem for every automotive industry. So it is still an open problem if someone want to solve it. So what is this problem is that it is a dynamic mass estimation problem, we call it. So we need to predict the mass of the vehicle. So there is one thing is that you directly keep the sensor. So but as we keep the sensor, the cost involves, and so many things are there, because sensors are for estimating the mass. We need multiple sensors. We need gradient sensor to know what is the grade, at what grade the vehicle is, what angle where vehicle is moving. So there are multiple problems. So one research paper we have written for this estimating the mass of the vehicle. So but our research paper is based on the physics based equations. But we believe that this problem can be solved using the AI techniques also, where we can where we think that we should load the vehicle in multiple with multiple means different weights, and at that time we should take the data and train the model that at this that this data corresponds to this load, and this data corresponds to this another load, and in the next time whenever the data will come, the trained model will tell that what is the load. So means that will be a machine learning model for detecting the mass. But this paper what we have written is a different paper. It just relies on the physics based equations. So there is a scope of new machine learning based algorithm for this. So Raman, can we go to next slide? So the one thing I would like to say that if anyone is interested in knowing that what are the recent trends going in the company or in any company, so you can directly go to this government website where all the copyrights whatever any company publishes, like you can see here where I have marked, there are two copyrights, Tata Motors. So this intelligent estimation of dynamic vehicle mass, this is the same, this is our copyright only what I was showing in the last. So the algorithm we have copyrighted, whatever the algorithm we had made. So you can directly search that any, it's like here you can see lovely professional universities, they have filed one copyright, in I think 2024 December to 24. So so you can directly go to these sites and directly check that in 2025 recent month is there any copyright from any automobile company. So you will directly come to know that directly what type of trends that on what things they are currently working. So this is a means like this you can come to know in every industry, automotive industry or any college, what are the patents or copyrights those people are working on. Or yes, Raman, next slide. So the same thing, the way we can use AI everywhere, because we know that for image classifications we use AI. So here in this AI, in this ADAS system, I myself have worked in is DMS for the testing of driver monitoring system, and one testing in the reverse parking, that for checking the reverse parking, how the reverse parking system is working or not. So there are use cases where we can use we can use this artificial intelligence, machine learning, and this neural networks very deeply, like in case of ADAS we do. Raman. And this is the same case is for BMS also. It is actually not for BMS, it is for every ECU, wherever is the data, wherever we are getting the data, we can do for everything, like um, state of charge estimation, y SOCs, hard and voltage. So these all are the terms. So the whole purpose is that, like the BMS, so battery management system. So currently here also we are working for the twin. So a digital twin is a concept when we where we try to replicate the complete model exactly, either in the MATLAB or in Python. It should be either database or physics based. So the purpose is that the way vehicle is behaving in the field, so the same way vehicle should behave in the model also, when we give the vehicle the same data what is going in the cloud. So suppose any fault occurred in any vehicle and vehicle got stopped. So what is the current situation? What we do is that we need to send the engineer to the field to monitor each and every aspect or each and every line of the bus. In this bus the resistance is this much, maybe this sensor is okay. We need to check each and everything in the bus to exactly know what is the fault or where the fault lies. But if we have the twin of the vehicle, suppose we made this battery twin of the battery, okay. So at that time what we will happen, we know that before fault all the data is coming in the cloud. So we will feed all that data to that model, that digital twin model. So that digital twin model will tell us that at which part the fault means, at what which part can be the faulty, because suppose there is a sudden surge of current because of some component, or because of maybe motor demanded some sudden current. So so at that time we can see those spikes in the current. So we will come to know that motor has demanded current, battery tried to full that demand, but before the battery there is some capacitor in the vicinity which tried to fulfill that demand of the motor, and because of that the relay or any sensor got failed. So like this complete, checking this thing in real time is very difficult task. So we have to go to, like in digital twin models, we need to make the model means exactly like if you are making the digital twin model of the battery, you need to simulate the chemical reactions of the battery exactly. Like in case of motor, you are making, if you want to make the digital twin of a motor, so you need to know all the aspect of MCU, and you need to the algorithms, whatever the algorithms are there for running, like FOC I think. And you need to model all the, like flux. There is one term flux in the motor. So we need to know the inductance, we need to know the resistances, that LD LQ maps we need to know, ID IQ maps we need to know, everything we need to know, then only we would be able to make these models. So making this digital model of any component is itself a very means very big task. But once we make that, we kind of protect our any, like battery we can protect, or we beforehand only we can know, using prognostics we can know which component is going to get failed, and there are so many things like this. So this much only from our slide. Over to you, Raman. uh, Raman, am I audible?
Hello.
Yes, Raman.
Yeah. So, like, anyone has any questions? Yes, I hope so. We are audible.
It's audible, sir.
Yeah.
Sir, which are the edge computing algorithms?
Yes, Chirayu, can you repeat your question once again? Which are the
Which are the edge computing algorithms?
uh, currently we are in aligned with a supplier, so directly machine learning algorithm we cannot use in edge, as the edge is limited. Edge devices are very limited in memory. So there is one term for that particular. I am missing that term. That is called. Mm, just give me some time, Chirayu.
Okay.
I will tell that. Actually, I will know. I will tell you that whatever are the general algorithms, the same algorithms we can run in the edge also, But the problem is of the memory and the processing power, because the edge is like the ECUs and BMS. Their memory is very restrained and limited, so we cannot run the heavy models, okay, in the edge. So there is one concept in what we called federated learning. Federated learning is a concept because, if you are training a model inside the edge, that is very difficult task. Difficult in the sense because of the memory constraint. So federated learning is a concept in which what we are doing, we take the data from the uh, from the edge. From the edge itself we take the data, we send that data to the cloud, we run the model in the cloud, we update the weights. We know whenever we run a algorithm, the weights get updated, weights and biases, everything must. A neural network means weights and biases, that's it, that's a number, a weight and bias. That's the whole meaning of a training a model. So there is a concept federated learning, where what we do is that we train the model in the cloud, and we just send the weights and biases back to the ECU. So model remains inside the ECU, just the weights are coming. So this is one method. This is called federated learning, the way we train the ECUs. Except there is one more term also, but I am not able to recall right now. Maybe I will tell after some. So one supplier is using that. So that another algorithm also we can use for this edge training.
Okay, sir. Thank you.
Yes, Chirayu, I just searched it. So actually, it is called Tiny ML. So the same time I was missing. So Tiny ML is a kind of machine learning only, but it is reduced terms. In reduced terms of memory, the machine learning takes so much times to train. So, but Tiny ML, tiny machine learning algorithms are the algorithms which are particularly made for the ECU by keeping the constraint by taking care of the constraint of the edge devices in terms of memory is less, processing power is less. So tiny machine learning algorithms it is called.
Okay, sir.
I guess so. This session would have been a little more, would have given a little more clarity towards what the industry is moving towards and what kind of research is expected from the industry, what kind of the use cases it can provide to the customer. There are various new technologies up, as well as AI plays a crucial role. But there are various other technologies as well, like DevOps and cybersecurity and connectivity, which is playing a crucial role in automotive industry currently. Feel free to explore new technologies. And if you have any doubts, you can ask. You can still get in touch with us through LinkedIn. Thank you, Tim. If there are any queries, uh, you can ask.
Participants, any queries? Thank you, sir. Thank you for sharing your innovative ideas for in the area of AML. The feedback link will be posted in the chat box. Participants kindly fill the feedback form. Thank you, Kodanram sir, as well as Pavan Joshi sir. Thank you very much.
Thank you everyone.
Thank you, everyone.
Thank you, sir.
Participants fill the feedback form posted in chat box. The next session will be started in 10 minutes.